Hello YouTube. This Acer Nitro worked fine until the DIY fan replacement somehow turned it into a paperweight. Let's find out what went wrong. So, the customer that sent this in reported that the owner replaced a noisy GPU fan, and they did so whilst the battery was still connected. After that, the computer powered on once, and then the screen went black, and it hasn't turned on since. So, let's quickly unplug the battery and see what current the board's drawing. Got my bench power supply set to 20 volts. I've got an Acer tip on my DC jack, so let's plug it in. 002. Oh, it's drawing 150 milliamps. Oh, guys, that's not good. It's not a good sign at all. Without a battery, I'd usually expect a board to be drawing around 10 milliamps, not 150. I wonder if anything changes when I hit the power button. Open it like that. No, it's solid at 150. There's no power LEDs or anything like that either, which is a pretty bad sign. So, 150 milliamps suggests we could have a short. We could start measuring with the multimeter, but that would take some time, and I'm feeling a little lazy today, so we're going to get out the lazy camera. Just let that boot up, and we can see if anything gets hot. Let's just change the temperature scale, so anything that does heat up is really obvious. There we go. There we go. So you can see, hopefully you can see, the outlines of the board components. And we'll be able to see a heat signature. So if anything goes orange, it means it's getting hot. Let's plug it in. And waggle the camera around. Oh, is that getting hot there? Plug it back in again, see if... Oh yeah, that instantly burns up. That's hotter than the sun. Okay, well, we don't need the thermal camera anymore. We know where the fault is. Let's get the microscope over the board in that area and see what's going on. I'm just going to double check this by dropping some IPA onto the chip and seeing if it's the chip itself that's getting hot or if it's a component nearby. Just put some on my fingers and touch the chip. That's all you need. And plug it in. Yeah, that's the chip that's getting hot. Why is the chip getting hot? So, could be a number of things. Let's get the multimeter out and look for the input. So, the coil will be the output of this regulator. And then there's the chip, and working backwards we have a little ferrite bead here, which is sort of acting like a fuse for the power input, and we've got two larger capacitors on the input as well. So let's check if that ferrite bead has a short to ground. Is it on 19 volts? No. Okay, that's got loads of resistance, so that's fine. And what about the output? Is the output shorted? Is that why it's getting hot? No. Okay, and do we actually have voltage going into the chip? I mean, we must do to some extent for it to be able to get hot, but let's turn the multimeter to DC voltage and plug it in again and see if we get input voltage. So we should have 19 volts here, and we do. What about output voltage? Nothing. Okay, so the coil's not shorted, the input's not shorted, it's getting power, but the chip's getting really hot. Why is it getting hot? What's going on? This is a pretty common thing to happen on a laptop board. So this is a 3 volt regulator. I've just checked the schematic. This is PU301 and this is the 3 volt regulator. It's quite common to see a 3 volt regulator getting hot like this on a laptop with no power. If you've been doing laptop repairs a little while, you probably know what's going on here. But for those that haven't, I'm going to try and explain it. Let's put the laptop to one side. We don't need this. So, This triangle with a plus in it is going to be your charger. This produces 19.5 volts. Most laptops it does anyway. And plugs into your laptop and then gets to the first MOSFETs. Once those MOSFETs are open, 19 volts carries on a little bit, and we get the high side rail. Now, the high rail sends power to all of the other regulator chips on the board. So we're gonna have a bunch. What they're gonna do is take 19 volts coming in and output voltage. So let's say this is 5. It will output voltage at a little coil and send it to the rest of the system. Now we're going to have a bunch of different regulators, so we can have 1.2 for RAM, and the one we really care about today is 3 volts. That's what we've been looking at with that chip that's getting hot. Now, what we need to consider is how much power is drawn when the laptop's off. We don't want to be powering most of the board when the laptop's off, so we're also going to need some... We don't want to be powering most of the board when the laptop's off, because that's just going to draw too much current and discharge the battery really quickly. So what we also need to do is create some low power circuitry that allows you to turn the laptop on without causing too much battery discharge. That's where this LDO line comes in. So we have another output from the 3 volt regulator, and that's called 3VLP. LP standing for low power. And then that goes off and powers the EC chip. I don't know what symbol. Let's make that a circle. Now, the EC chip is the embedded controller. Some people know it as a Super I/O or a KBC, which is keyboard controller. It does a lot of things. It controls the keyboard. It controls a lot of the power sensors. It powers the fans. Well, no, it doesn't. It senses the fans and tells them how fast to spin. It senses temperatures. It basically controls a lot of what your laptop's doing, including input to the power button. So, this doesn't draw much power, but whilst drawing very little power, it will allow the laptop to respond to the power button being pressed and turn on. What happens if the EC is short? Too much power is going to be drawn through the 3 volt regulator, and because of that, it's going to get hot. So I think that's what's happening. I think we have a short on 3VLP, and as a result, the 3 volt regulator can't drive that line, therefore it's getting hot. Hopefully I didn't butcher that explanation too much, but let's get the laptop back on the bench and get under the microscope and give you a bit more light. And now from looking at the schematic, I think this is going to be the pin for 3VLP. I'm going to this capacitor here. And it's 5 ohms to ground, which is no good. So, short on this 3VLP output means this regulator is getting hot. Now before I go any further, just gonna have a look at the fans. This one looks kind of dusty, so I'm guessing, yeah, and they said this is the CPU fan, and they said they replaced the GPU fan. So this one's not been replaced. Let's check the GPU fan. And I'm just going to quickly check resistances to ground on these pins. So we should have 4 pins here. One's going to be positive voltage. Then we're going to have a PWM signal, a tachometer, and a ground. That white mark there designates pin 1, so pin 1's ground, followed by either PWM or TAC, which is fine. Same again, that one's fine, and positive voltage is okay. And on the other fan, let's see. Ground is ground, which is exactly what we expect. Oh, that's 28 ohms to ground. That's low. That's lower than the other one. That's okay. And the fan power is okay. So I was measuring these to see if we could spot anything that might have happened that has led to this fault. And 28 ohms to ground on that signal is low. It's kind of strange that it's on the fan that they haven't replaced. Let's just unplug this cable and see if that resistance goes up, because there could be an issue with this fan causing that low resistance. No, it's still short. Okay. That's strange. Let's have a quick look at the schematic. And pin 2 of the fan connector is fan speed 1. So I'm going to hazard a guess that that senses the fan speed and reports it back to the EC chip. And yeah, it goes straight back to the EC chip. Coincidentally, the EC chip is also powered by 3-volt low power, which is the other signal that we found a short on. 2 short circuits feeding the same chip. It's fairly safe to assume that we have an issue with the EC chip. So let's take the board apart, find the EC chip, and remove it. We can see if that lifts the shorts. Oh, I've left the screen cable plugged in. Can't be having that. Okay, board is out. And according to the schematic, this has a... What EC chip does it have? It has a KB9542Q. So we're going to be looking for... Oh, it's under the SSD. Didn't even need to take the board out, really. There it is. Let's remove the Wi-Fi card, because we're going to be heating this area. And there we go. Can you read that? KB9542QG. Let's remove that and see if the short's lift. That sticker's going to melt, but who cares? I'm not going to bother adding flux to this chip as I remove it. Whoever said you need to add flux to a chip you're removing and throwing in the trash was lying. Let's go to 380 on the heat gun and max my airflow. Why not? Doesn't want to budge, so I'm going to turn the heat gun up just a little bit. There we go. Hey, would you look at that? The sticker didn't melt. That's nice. So, the EC chip is off. All the pads are cleaned up. And let's go back to our short circuit. So, 3VLP. is now 3.5k. That's good. And that line is now open line. So, that seems to have lifted our short circuits. So we can get on with replacing this EC chip. And once that's done, we get to the real fun part. Where was pin 1? Top left. Like that. That little white square matches that dot. This EC chip came off a donor board, so hopefully it works. I don't actually know. So I'm just going to get that vaguely into place, and we can tack the corner down with a bit of solder. Make sure it actually bonds with the legs. And get the next corner in alignment, so that looks okay. Now we've got a couple corners. Oh no, that's slightly out of alignment down here, so just gonna see if I can move that a little bit. Yeah. That's good enough for me. It's not perfect, but it will do the job. So I'm gonna go in and start soldering each side. I'm gonna move the board so it's a bit more comfortable. We can start with this side here, the right hand side, because I'm right-handed. Get some solder on there and just lightly brush against these pins. I don't think that's quite enough solder. Let's zoom in just a little bit more. Add a bit more flux. And that row of pins all looks okay, other than that solder short on the first two. So we go to the next side. Just adding flux when we think we need a little bit more. And if we're not sure that our pins are soldered, we can just take a pair of tweezers and just lightly tap the pins. If they move, they are not soldered. So you'll see this one, if I tap it, you see how it moves around. That's not good, but we haven't tried soldering that yet. So let's get you in focus. And solder this side. That looks okay. And the last side. And that looks pretty good. I don't think any of the pins are loose or have any solder shorts, so let's clean that up. And there we go. EC chip has been replaced. It's pretty straightforward, really, until you get to the part where you realize it has firmware on it. So this chip is programmed specifically for the board it's on. Or in my case, specifically from the board we stole it from. Which probably isn't going to work with this motherboard. So let's just do this as a proof of concept, because I could be wrong. This might work. It did come off another Acer board, but it came off a Nitro that had an AMD Ryzen CPU. This is an Intel system, so this is quite a difference in architecture. Could have similar firmware. So plugged it in, it's drawing 22 milliamps. Oh, now down to 3. And there's a power switch jumper down here, I think. I think that is a power switch jumper. Let's see what happens when I press it. Power goes up to 34. Maybe that's not the power button. I'd expect it to be though. What about the keyboard connector? Is there a power switch jumper near there? No. Okay, well I'm going to look at the schematic and just confirm what SW1 does, which is the pad I was just shorting out. Then we've got to see what we can do next to see if we can bring this laptop to life. Okay, yeah, so this switch says it's the on-off button. Let's just make sure we get 3 volts to it. I suppose I haven't yet checked that we've restored our 3 volt low power, but the current looks about right. So yeah, that's the power switch. It's got 3 volts on it, and if I jump it, nothing happens. Oh, the current's changed a little, but not enough. So what's probably happening here is this EC chip doesn't have the correct firmware for this board. We've got to figure out how we can fix that. So the EC chip, as I said earlier, is also known as the keyboard controller because it interfaces through the keyboard connector with the keyboard and recognizes any inputs. But there is a useful secondary feature. We can program the firmware from this EC chip through the keyboard connector. To do that, we need one of these. This is an EC programmer. This is the Vertyanov EC programmer. There are other programmers available, but this is what I have. And this is its little breakout board that goes into it here. And then we have 3 connectors of different sizes that we can hook up to a motherboard through the keyboard connector's ribbon cable. So the way we're going to interface with this is first look at the connector itself. And we're going to see roughly what size the connector is, see how many pins are on it, and then we should be able to pick out the right flex ribbon cable to connect the programmer to the board. So this flex cable, I think, is a 30 pin or a 32 pin. And the keyboard connector, does it match? So I'm just going to line the pins up there. And you can see it roughly matches that. So I think this is the correct number of pins and the correct pin pitch. And on the other end of our programmer, we have 1 mil, 0.8 mil, and 0.5 mil. And this cable is a 0.5 mil, so it matches up with this connector. So what we're going to do is we are going to connect our cable, which is, it's actually can be a little tricky, because if you see, the cable has loads of room either side of it. It's very easy to misalign. So we'll try and plug that in straight. And then we're going to do the same on the other side with the EC program. And we can test to check continuity between pin 1 of the keyboard connector and pin 1 of the programmer. And we have 0 ohms, which is good. What about pin 32 and 32, 0 ohms? Perfect. So let's just cover this in a bit more detail. You'll see what I mean later, but this white dot represents pin 1 of the keyboard connector. And the reason I've checked continuity is because you can plug the cable in this way, or you can plug the cable in this way. So it depends on the type of keyboard connector, but some have contacts facing down and some have contacts facing up. This one has contacts facing down, so this cable wants to be in this way round. If we had no continuity, then of course we'd want to flip the cable, but what that would do is create all of the signals crossing. So pin 1, with this cable flipped, would now be connected to pin 32 of the programmer. Now, this is important, and I'll show you why in software later, but it's important you get all this right. The next thing we're going to want to do is ground our programmer. So this programmer has two USB-C ports. One is to ground to the board you're programming, and one is to connect to the computer that you want to use to program it. So I'm going to hook the USB-C port to its ground, and then we can grab a cable, grab my laptop, and hook up the remaining USB port to my laptop, and I'll show you it in software. Now we've got everything hooked up other than power to the laptop board, we can go and open our Vertyanov successor programming suite. And this chip is an ENE, I think, KB9542. So we're going to select mode, go to IT ENE Nuvoton, click ENE, and we're going to search for the model of our motherboard. This one is LA-L978, and they don't have it, which is not good. I was worried about this. Yeah, this motherboard's an L978P. So what we could do is type in KB9542, and we already know that it's 0.5 mil with 32 pins. See if we can find anything that's remotely close, and we can't. So what do we do when we want to program an EC chip, but we don't know what pin's what? We need to go to the schematic, we need to check which pins do what, and we need to write our own. So an example here is we need on this EC chip pins KSI3, KSI4, KSI5, 6, and 7. Well, on this one, yeah. So we need to find where they are on the keyboard connector, and then if we go into our successor folder and we open MB connection ENE, we have this. So this is all the boards that it has in the database. For example, LA9063 has 30 pins. Pin 1 is on the left hand side. The pin pitch is 1 millimeter and it's facing down. And then each of these represents a signal on the EC, and the equals and the number after it represents the pin number on the keyboard connector itself. So KSO3 is probably like pin 60 of the EC, for example, but it's routed to pin 13 of the keyboard connector. So what we need to do is find out where that signal is on our board and write a new line like this for it. So let's get started. We've got LAL. Let's put it roughly in the right place. LAL 978P. KB underscore pins equals 32. The pin 1 is on the left side of the connector, and the cable faces down. It's 0.5 millimeter pin pitch, and I mean it could be similar to this one above it, but that says it's got a different chip, 9052. But let's have a look at the diagram for this board and see if we can see where KSO3 is. Let's just, to start with, let's just paste this in there. So, the chip we know is a 9542Q. Okay, I finally got the schematic up. Let's Control F and search for JKB. That's usually what it's called. JKB1. There we go. Took a second that. If we zoom in, this is the keyboard connector. So if we go back to our notes, we can have a look. Where are we? So KSO3 is currently designated to pin 23, and we can look pin 23 on this is KSO3. Okay, what about the next pin? KSI4 is pin 6, and if we go here, 1, 2, 3, 4, 5, 6, KSI4 is pin 6. Perfect. And we can just keep going through that, checking each individual pin until we know that all of these are allocated to the right place. So KSI7 is pin 3, okay, 6 pin 4, and 5 pin 5. All looks good. Okay, so it turned out that the LAL978P board is the same keyboard connector layout as the LAL973. But that's how you write a new chip and a new connector into the database for the Vertyanov successor. It can be really helpful, especially if you get a schematic or a board view, to be able to do this, because you can't always find out how to program these boards. So let's save that. Now we've edited it, and we can get rid of that and go back to the software. We're going to have to restart the software for that new database entry to load. Go back to, it's not an ITE, it's an ENE. Go back to the right setting, and we can now type LAL978P. For some reason that didn't recognize, but that's fine. And then hit apply settings. It's going to ask us what type of cable we used, so we used a 32 pin, single-sided, and then it's going to show us a nice little picture of how we plug it in. With all that set up, hopefully set up correctly, what we can do is plug in the motherboard, and shortly after plugging in the motherboard, hit get ECID. Hey, and it's recognized, that's good. Now I'm pretty sure this is a 128K, so I'm going to take a read of this original file. Let's hit read there, and let's save this to desktop as Acer Nitro EC old. Cool. Now we have the next set of problems. How do we get the EC firmware if we can't find it on any forums? So let's start. We've taken a read of the original. Even if it's a new chip, it's going to have something on there, and it's good to take a read of what you originally have there. Now let's put it into hex and take a look. Just going to have a quick scroll through and see if there's any recognizable characters there. It says 954X. It's a little bit into it. Sometimes they say ITE. If it's an ITE keyboard controller, it might say ITE in this ASCII area here. But this is an ENE, and it says 954X. So what we're going to want to do is try and find a BIOS file for this model of laptop, and then we're going to search that file for 954X. Most of the time, a BIOS file for a laptop will contain a backup of the EC firmware, so that's a good place to find it. So let me have a look if I can find the BIOS file. Now I'll pause the video here and be back in a second. Okay, we're back, and we have a BIOS file loaded up in hex as well. And we're just gonna go over to that file, Control F, and go 954X. And there it is. So this is the EC firmware that's within the BIOS file. Now, what should we do? We want to find where this file starts. So it starts shortly above it. See if we can replicate similar. How long does this go for? Does this one start here? Looks like it starts with a 020F. 020F. Yeah, that could be okay. Now we want to know what the length is. So if I hit Control A, the length is 20000, or 128 kilobytes. So on this one, I'm going to hit Control E, select length, 20000. That was the right number of zeros, right? Yeah. Now let's open a new hex file, paste insert, and there we go. That's our EC firmware extracted. So let's save this as new EC and go back to Vertyanov software. Go back to LAL978P. Tell it all the info that it needs to know. Get ID. Load file. Open the new file that we've created, extracting the EC from the BIOS. And right. That seemed to happen successfully, verified successfully. So I'm going to stop the video here, reset up the cameras and the bench supply and see what it does. So there we go. The EC is all programmed up. And if you press the power button switch, you can quite clearly see nothing is happening. So, where did I go wrong? So, I've been scratching my head a little bit, and I think I know what I did. I replaced the original EC chip, which is KB9542QG, with a different one. I replaced it with QF2. So there's a couple digits at the end. I didn't pay enough attention, I didn't get the right chip, and now we've got to start the entire process again. So I don't have one of these in stock, I'll have to order one in, and we'll pick up the video there. So, we're finally back, and hopefully, in here, I have the actual correct EC chip. It's been a while, I had to buy it from China, and it took a while because it was Chinese New Year, so I sort of forgotten where we were. I think we had fitted the EC chip and programmed it, and then I realized that it was actually a slightly different revision of chip. So we're going to start over again and fit this EC chip. I'm going to program it off camera. You've already seen how it's done. And we're going to see if the board works. So let's get on with it. I'm going to blast it with some heat, remove it when the solder's melted, and we can drop the new one on and solder that in place. It's been so long since I started recording this video that I changed my microscope light, and I've also changed the way I capture audio. So if the audio sounds better and the video looks cleaner in the second part of the video, then that's why that is. Just gonna use some wick with a bit of flux on it to clean up the pads without scratching anything. And I tombstoned a resistor just here. Got the shakes this morning. So I just pop that back down. Or at least try to. Same as before, bit of flux. Not too much. And then we can drop the new chip on. Dot going to the dot, which denotes pin 1. Try and get all 4 sides lined up. Just holding it down with my finger. And now we can just tack in a couple of corners. Make sure it doesn't move anywhere. Looks okay. Looks maybe a bit reflective. Let's turn my light down just a touch. It's nice to be working on something that's not a graphics card. Not a lot of graphics cards recently. You can solder an EC chip a bunch of different ways. You could just make sure there's solder on the pads and flow it on there with hot air. But I always prefer to solder by hand with these for some reason. Just reduces the chance of thermal shock or damaging the chip. Well, the pins seem solidly soldered on, so let's clean that up. I really do hope this works after reprogramming. Otherwise, I don't know what's going on with this board. It should be quite a simple fix, given the original fault stemmed from a defective fan. I guess it could have sort of done some damage to a signal elsewhere, but I'm pretty confident that this is going to work. Well, that should do. Chip is on, so I'm just going to fly it through some programming, and then going to pick up after it's been programmed, and hopefully this thing works. So I went to program the EC chip, and I noticed something I missed first time round. So first time round, we assumed that this was 128K. So first time round, we assumed the EC file was 128K. It seemed to end at around 128K. There seemed to be no more data after it, or at least there was a gap in the file. So I just assumed 128K. But now I'm revisiting it, I realised that we don't actually know that it's meant to be 128 KB. Some EC chips, after the part number, they'll say 128, 196, 256, and that will denote how much storage they have. This one doesn't, so we don't actually know. I could probably Google it and it would probably tell me, but so there is a better way of getting the EC file directly from a BIOS, and we can do that by using a manufactured downloaded BIOS and something called BIOS utilities. So I'm going to go back to my PC and I'm going to talk you through what I did to get the full EC file and not just randomly guess what size the EC file was meant to be. So let's go back through extracting some EC firmware. This time we've downloaded the BIOS file directly from Acer's website. It's not downloadable in a bin format, so we don't get the full BIOS file. What we get is this application. And what we need to do is extract this application so we can get access to all the data inside it. Now if we try and launch it, run anyway, it's probably, it's going to extract somewhere in temp, probably, and you might be able to find that, but I don't think it'll give us the option to actually extract the contents. Nope, does not support. Okay, that's because this is a different computer. Even if we could extract it, it might not extract in the way we want it to. So this is where BIOS utilities come in. You can get this downloaded from GitHub, it's free. It's a bit of a faff to install. There's some other dependencies like Python and stuff like that, but I think all the info's there on the GitHub page, and it links to everything that you need. And once you've got it in and working, let's drop this into the main script. Just going to bring up a Python window, and if I ignore this directory path, it's just going to create a folder called extracted. So let's just hit enter, and okay, that all looks done. Press any key to exit, and now we've got a folder showed up in its root called extracted, and got all this stuff, which is the application and other rubbish. But inside these files here, we have two different BIOS versions in this package, and both of them have a full image, the EC controller, and a clean ME region. So what we care about is the EC controller in this case, and as you can see, unlike the file that I originally tried to program, it's 160 KB. We tried to do 128 before, so I definitely programmed the wrong size. This is a really good way of getting the EC firmware without having to mess around in hex too much. You just drop that file onto BIOS utilities it extracts it all for you. And then you've got a full clean EC file direct from the manufacturer. So I'm just going to copy and paste that onto a memory stick, go back over to my other PC, and we'll get that programmed up. So we just want to clarify here that the two different ways of extracting an EC file I showed you are both effective and totally working ways of doing this. It's just if you extract it just in hex, you need to make sure you extract the right amount of data. I have programmed the EC chip again, this time with the full 160 kilobyte file. Let's plug it in and see what it does. Right, so there's power pads. Can't remember if I showed you them before. There's a SW1 noted on the board, and that is a debug power switch. So let's just jump those 2 points with tweezers, and it's turning on. It's drawing 1.6 amps, which is all I needed to see. Let's unplug that and get the board back in the chassis, see if it posts, see if it displays anything. For now, I don't think I'm going to plug the fans in, just because we know that the fans led to the blown EC chip, and we don't really know if they're working, and I simply just don't trust them. So what I might do is, for the sake of safety, order in a new set of fans before we fully test this unit. Because the last thing I want to do is plug these fans in again and have them blow out the EC chip, because then we don't have to do the work again. So we know it was the left fan that had the shorted PWM line. So the right fan's probably okay, but you know, I might just replace them both, because I don't know where they got that from. I don't know if it's got any problems. And as I say, I don't want to have to redo all of this once more. I only bought one EC chip, so I don't want to kill it. Let's leave the battery unplugged for now. It shouldn't overheat before it posts and turns on. Even with no fans, it should stay cool enough to do what we need to do. Let's plug it back in, and hopefully we get picture. Oh, my DC jack is not in the best condition, so let's try and get it into the right place where you're going to be able to see. And hit the power button. This chair makes a lot of noise. I need to fix this chair. I'll get a new chair. It's very squeaky. Hopefully it's not ruining the videos. So this will take a while to post. It's had a CMOS battery port, so it has to complete memory training and that sort of thing, and it'll cycle on and off a couple of times before it decides to display. But things are looking like they're heading in the right direction. You can see the current bouncing around. It's not stuck at any point, and it's doing a couple of boot cycles, 2 or 3 usually. Sometimes certain machines, like Alienware's, can take a very long time to go through this process, but hopefully this turns on soon. Yes, it works. I'm going to close that lid before you seal the user's data and their name, but that's that. It is working, it is turning on, and it is booting Windows. So, we have another repair completed. I did get tripped up by a couple of things. So first thing, I used the wrong EC chip. Now, I do wonder if that would have worked if I'd flashed it with the correct size file originally, but who knows, who cares? It's probably smartest to use the chip with the matching numbers. Secondly, I flashed the wrong size file. I assumed wrongly that it was 128 KB, and it's actually 160, which is why BIOS utilities and the BIOS extraction feature that can be really handy for grabbing things like EC firmware from a board where you can't find the resources online. But despite all our mistakes, we got there in the end. I hope you learned something. I hope you learned a bit more about EC programming. Hopefully this will help some people to use the Vertyanov programmer and maybe struggle a bit connecting to boards that don't have listed support, or struggle to find EC files. So anyway, thanks for watching. I hope you enjoyed this video, and as I say, hopefully you learned something, and I will see you next time. Yeah, there we go. It's on the log on screen. Perfect.